Hi, my name is Daria, and my partner Andy and I will be talking about the effects of global warming on precipitation. For reference, here are the definitions of the variables used in our derivation. The atmosphere energy balance dictates that precipitation equals evaporation, which is equal to the sum of the net radiative flux plus sensible heat over the latent heat of evaporation times -1. We also have the equation for the Bowen ratio. Now, assuming the surface air is saturated and the difference in air and surface temperatures is relatively small, we can take the partial derivative of saturated specific humidity with respect to temperature and obtain the following equation. From here, we can manipulate the equilibrium Bowen ratio, and now we will use the assumption that specific humidity of the surface is equal to the saturated specific humidity of the surface. Substituting the equations from the previous slides, we get the following form of the Bowen ratio. Now, through the rest of the lines, we use some algebraic manipulations along with substitutions from the previous slide to find the Bowen ratio in terms of the equilibrium Bowen ratio in this bottom equation. Now we will change gears and discuss the surface energy balance, which is the first equation on this slide. After some more algebra, we get this equation here, and using the fact that sensible heat divided by latent heat gives the equilibrium Bowen ratio, we can substitute that into this last equation. Now using the evaporation rate equal to the LE over E, and the second equation, which is the equilibrium evaporation rate, we can now substitute in again the Bowen ratio, and after some more algebra, end up with this equation down here. Now I'll hand it over to Andy for the second half.
Okay, let's continue the derivation from the surface energy balance. The bulk aerodynamic formula defines the latent heat of the water, which is the equation right here. Then we substitute into the previous equation, we get the following. We substitute in this part. Then rearrange the term a little bit, we get the EEN and the E air. EEN is the part that compensates the latent heat, including the radiative flux, horizontal flux, and the storage. The E air, on the other hand, is the capacity of the air to take on water. Let's only focus on the E air part. Rewriting the humidity of the air according to relative humidity, we have the new way to representing the E air, which is here. We assume the saturated surface before, which is the condition for max evaporation to occur. This is called potential evapotranspiration, or PET. PET is just a fancy word for the capacity to take air by to take water by air. And the following four equations are the same as before. Write PET in terms of relative humidity. Then we do the derivation to prepare for the next part, to introducing the equilibrium Bowen ratio into the equation. Next, let's take the derivative respect to the surface temperature. Assuming the wind speed, relative humidity, and the surface air temperature difference don't change much, then we get the last equation. Note the Bowen ratio, the equilibrium Bowen ratio is also depending on the surface humidity. Ultimately, we need to know the relationship between the saturation humidity and the temperature. We can find the relationship in many ways, either empirically or following the Clausius Capron equation. Looking at the graph, as the temperature goes up, we know the saturation, humidity, and the inverse of the equilibrium Boeing ratio rises exponentially. Therefore, the rate of the PET increase exponentially, which means the air moves more moisture from place to place. However, the annual precipitation does not increase globally because the net radiative flux constrained. Therefore, the wet place will rain more and the drier place will rain less. In other words, the wet place will get wetter and drier place will get drier. Yeah, that's it. Thank you everyone for listening.